Ground to neutral voltage, also known as neutral to ground voltage, is the voltage difference between the grounding system and the neutral conductor in an electrical circuit. High ground to neutral voltage can be caused by several factors. Firstly, harmonic currents. Nonlinear loads, such as electronic devices and fluorescent lighting, can generate harmonic currents that flow through the neutral conductor. This can create a voltage drop on the neutral, resulting in an elevated ground to neutral voltage. Secondly, asymmetrical loading. When different phases of a three-phase system carry unequal loads, the neutral current increases, which can also cause a voltage drop on the neutral. Thirdly, loose or poor connections. Loose or corroded connections at electrical outlets, panels, or grounding rods can increase the electrical resistance of the neutral path, leading to a voltage drop. Fourthly, ground loops. A ground loop occurs when there are multiple paths for current to flow back to the grounding system. This can result in circulating currents and elevated ground to neutral voltage. High ground to neutral voltage can interfere with the operation of sensitive electronic equipment, such as computers and medical devices. It can cause data corruption, slow performance, and even damage. To mitigate high ground to neutral voltage, several strategies can be implemented. Firstly, use balanced loads. Distribute loads evenly across all three phases of a three-phase system to minimize asymmetrical loading. Secondly, install harmonic filters. Install harmonic filters to suppress harmonic currents. Thirdly, check and tighten connections. Ensure that all electrical connections are tight and secure. Fourthly, eliminate ground loops. Locate and eliminate ground loops by ensuring that there is only one path for current to flow back to the grounding system. Fifthly, separate circuits. Run separate circuits for sensitive electronic equipment and avoid plugging them into the same yoke as high current devices. Elevated ground to neutral voltage is not uncommon, especially in commercial buildings where there are high concentrations of electronic equipment. The level of ground to neutral voltage that is considered acceptable varies depending on the sensitivity of the equipment and the industry standards. High ground to neutral voltage can be an issue for sensitive electronic equipment. By understanding the causes and implementing mitigation strategies, electrical contractors can minimize the effects of this voltage on the operation and performance of equipment. It's crucial to understand the underlying principles of electrical grounding and bonding to effectively diagnose and address ground to neutral voltage issues. The grounding system provides a low impedance path for fault currents to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers and fuses. Bonding ensures that all metallic parts of the electrical system are at the same electrical potential, minimizing the risk of electric shock. When troubleshooting ground to neutral voltage problems, it's essential to use appropriate test equipment, such as a true RMS multimeter or a power quality analyzer. These instruments can accurately measure voltage and current under non-sinusoidal conditions, which are often present when harmonic currents are a contributing factor. Start by measuring the ground to neutral voltage at the main electrical panel and at various branch circuit receptacles. This will help you identify whether the problem is widespread or localized to a specific area. A high ground to neutral voltage at the main panel may indicate issues with the utility supply or the grounding electrode system. If the voltage is within acceptable limits at the main panel but elevated at certain receptacles, the problem is likely within the building's electrical system. Inspect the neutral conductor for loose or corroded connections. Pay close attention to connections at the main panel, subpoles, and receptacles. Use a torque screwdriver to ensure that all connections are tightened to the manufacturer's specifications. Check the grounding electrode system for proper installation and condition. The grounding electrode should be a continuous, low-impedance path to earth. Verify that the grounding electrode conductor is properly sized and connected to the grounding electrode. If the grounding electrode is a ground rod, ensure that it is driven deep enough into the earth to provide adequate grounding. In situations where harmonic currents are suspected, use a power quality analyzer to measure the harmonic content of the current flowing through the neutral conductor. If the harmonic content is excessive, consider installing harmonic filters to reduce the level of harmonic currents. Harmonic filters are designed to shunt harmonic currents away from the neutral conductor, reducing the voltage drop and improving power quality. Asymmetrical loading can be addressed by redistributing loads more evenly across the phases of the electrical system. This may involve moving circuits from one phase to another or installing additional circuits to balance the load. Use a clamp-on ammeter to measure the current on each phase and adjust the loads accordingly. Ground loops can be difficult to locate and eliminate. Start by identifying all possible paths for current to flow back to the grounding system. This may involve tracing the grounding conductors from various pieces of equipment back to the main panel. Once you have identified the ground loops, you can eliminate them by disconnecting one of the grounding paths. Be careful not to create a safety hazard by disconnecting a grounding conductor that is necessary for equipment grounding. In some cases, it may be necessary to isolate the grounding systems of different pieces of equipment to prevent ground loops. This can be achieved by using isolation transformers or optical isolators. When running separate circuits for sensitive electronic equipment, use dedicated neutral and grounding conductors. This will minimize the potential for noise and interference in the neutral conductor, which can contribute to ground to neutral voltage. Ensure that the dedicated circuits are properly sized to handle the load and that the conductors are installed in accordance with the National Electrical Code NEC. In addition to the above strategies, it's important to educate building occupants about the causes and effects of ground to neutral voltage. Explain how their actions, such as plugging multiple high current devices into the same circuit, can contribute to the problem. Encourage them to use energy-efficient appliances and lighting, which typically generate fewer harmonic currents. Regular electrical inspections and maintenance can help prevent ground to neutral voltage problems from developing. During inspections, check for loose connections, corroded conductors, and other signs of electrical distress. Perform infrared scans of electrical panels to identify hot spots, which may indicate loose connections or overloaded circuits. By taking a proactive approach to electrical maintenance, you can ensure that the electrical system is operating safely and efficiently. When dealing with sensitive electronic equipment, it's important to follow the manufacturer's recommendations for grounding and wiring. Some equipment may require special grounding techniques or dedicated circuits to ensure proper operation. Consult the equipment's installation manual for specific instructions. In some cases, it may be necessary to install an isolated ground receptacle for sensitive electronic equipment. An isolated ground receptacle has a dedicated grounding conductor that runs directly back to the main panel, bypassing the building's normal grounding system. This can help reduce noise and interference on the grounding conductor, improving the performance of the equipment. It is important to note that the NEC has specific requirements for isolated ground receptacles, so be sure to follow these requirements when installing them. Another important consideration is the type of wiring used in the electrical system. Solid conductors are generally preferred over stranded conductors for grounding applications because they provide a lower impedance path for fault currents. However, stranded conductors may be necessary in some situations, such as when wiring flexible conduit. When using stranded conductors, be sure to use the correct type of crimp connectors to ensure a secure and reliable connection. The NEC also specifies the minimum size of grounding conductors based on the size of the ungrounded conductors. Be sure to consult the NEC to determine the appropriate size of grounding conductors for your application. In addition to the NEC, other industry standards and guidelines may provide additional information on grounding and bonding. For example, the Institute of Electrical and Electronics Engineers IEE has published several standards on grounding and power quality. These standards can provide valuable guidance on designing and maintaining electrical systems that are free from ground to neutral voltage problems. When troubleshooting ground to neutral voltage problems, it's important to document your findings and keep a record of all measurements and repairs. This will help you track the progress of your troubleshooting efforts and identify any recurring problems. It will also be helpful to have a detailed understanding of the building's electrical system, including the location of all panels, circuits, and grounding electrodes. This information can be obtained from the building's electrical drawings or by performing a thorough inspection of the electrical system. In some cases, it may be necessary to consult with a qualified electrical engineer to resolve complex ground-to-neutral voltage problems. An electrical engineer can perform a detailed analysis of the electrical system and recommend appropriate solutions. They can also help you ensure that your electrical system is in compliance with all applicable codes and standards. By following these guidelines, you can effectively diagnose and mitigate ground-to-neutral voltage problems, ensuring the safe and reliable operation of sensitive electronic equipment. Remember that electrical work can be dangerous, so always take appropriate safety precautions and consult with a qualified electrician if you are not comfortable performing the work yourself. Furthermore, understanding the role of the neutral conductor in a three-phase system is paramount. In a balanced three-phase system, the neutral conductor ideally carries little to no current because the currents in the three phases cancel each other out. However, in reality, perfect balance is rarely achieved due to variations in load distribution. This imbalance leads to current flow in the neutral conductor, which contributes to voltage drop and ground-to-neutral voltage. The impedance of the neutral conductor is a critical factor affecting ground-to-neutral voltage. Impedance is the total opposition to current flow, including both resistance and reactance. Resistance is the opposition to current flow due to the material of the conductor, while reactance is the opposition to current flow due to the inductance and capacitance of the conductor. A higher impedance neutral conductor will result in a larger voltage drop and a higher ground-to-neutral voltage. To minimize the impedance of the neutral conductor, it's important to use conductors that are properly sized and have low resistance. Copper conductors are generally preferred over aluminum conductors for grounding and neutral applications because they have lower resistance. The length of the neutral conductor also affects its impedance. Longer conductors have higher impedance due to the increased resistance and inductance. To minimize the length of the neutral conductor, it's important to locate subpanels as close as possible to the loads they serve. The grounding electrode system plays a crucial role in maintaining a low ground-to-neutral voltage. The grounding electrode system provides a low impedance path for fault currents to return to the source, as well as a reference point for the electrical system. A properly installed and maintained grounding electrode system can help minimize ground-to-neutral voltage by providing a stable and reliable ground reference. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, crown plates, or metal water pipes. The grounding electrodes are connected to the grounding electrode conductor, which runs to the main electrical panel. The NEC specifies the minimum size and type of grounding electrodes, as well as the requirements for their installation. In addition to the grounding electrode system, the bonding system is also important for minimizing ground-to-neutral voltage. The bonding system ensures that all metallic parts of the electrical system are electrically connected together, creating a common ground potential. This helps to prevent voltage differences between different parts of the electrical system, which can contribute to ground-to-neutral voltage. The bonding system typically consists of bonding jumpers, which are used to connect metallic parts such as conduit, equipment enclosures, and water pipes. The NEC specifies the requirements for bonding jumpers, including their size and installation. When troubleshooting ground-to-neutral voltage problems, it's important to consider the effects of electromagnetic interference, or EMI. EMI is electrical noise that can interfere with the operation of electronic equipment. EMI can be caused by a variety of sources, including radio transmitters, microwave ovens, and fluorescent lights. EMI can couple onto the neutral conductor and contribute to ground-to-neutral voltage. To minimize the effects of EMI, it's important to use shielded cables and connectors. Shielded cables have a metallic shield that surrounds the conductors, which helps to block EMI. Shielded connectors are used to connect shielded cables together and provide a continuous shield. It's also important to keep sensitive electronic equipment away from sources of EMI. Power conditioning equipment, such as surge suppressors and line filters, can also help to reduce the effects of EMI. Surge suppressors protect electronic equipment from voltage spikes and surges, while line filters remove noise and interference from the power line. In addition to addressing the causes of ground-to-neutral voltage, it's also important to address the symptoms. One common symptom of high ground to neutral voltage is data corruption. Data corruption can occur when voltage fluctuations on the neutral conductor interfere with the operation of electronic equipment, causing errors in data transmission and storage. To prevent data corruption, it's important to use uninterruptible power supplies, or UPSs. UPS provide backup power to electronic equipment in the event of a power outage, as well as voltage regulation and surge suppression. Another common symptom of high ground to neutral voltage is equipment malfunction. Equipment malfunction can occur when voltage fluctuations on the neutral conductor damage sensitive electronic components. To prevent equipment malfunction, it's important to use equipment that is designed to withstand voltage fluctuations. It's also important to perform regular maintenance on electronic equipment to ensure that it is operating properly. When addressing ground to neutral voltage problems, it's important to take a systematic approach. Start by identifying the symptoms, then investigate the causes, and finally implement solutions. By following this approach, you can effectively diagnose and mitigate ground to neutral voltage problems. Remember that electrical work can be dangerous, so always take appropriate safety precautions and consult with a qualified electrician if you are not comfortable performing the work yourself. The interaction between different grounding systems within a facility can also contribute to elevated ground to neutral voltage. For example, if a building has separate grounding systems for the electrical power system and the telecommunications system, a potential difference may exist between these two systems. This potential difference can drive current through the grounding conductors, leading to ground to neutral voltage issues, particularly affecting sensitive telecommunications equipment. To mitigate these issues, it's often recommended to bond the different grounding systems together to create a common ground plane. This involves connecting the grounding electrodes of the various systems together using appropriately sized bonding conductors, as specified by the NEC. Creating a common ground plane helps to equalize the potential between the different systems, reducing the flow of current through the grounding conductors and minimizing ground to neutral voltage. In addition to bonding different grounding systems, it's also important to consider the grounding of sensitive electronic equipment. Some electronic equipment may require a dedicated grounding conductor that is isolated from the building's normal grounding system. This is often referred to as an isolated ground. An isolated ground provides a low impedance path for fault currents to return to the source, while also minimizing the amount of noise and interference that is coupled onto the grounding conductor. Isolated grounds are typically used for equipment that is particularly sensitive to noise and interference, such as audio equipment, video equipment, and computer equipment. The NEC has specific requirements for isolated grounds, including the size and type of grounding conductor that must be used. Another factor that can contribute to ground to neutral voltage is the presence of DC current on the neutral conductor. DC current can be caused by a variety of sources, including rectifiers, inverters, and other electronic devices. DC current can saturate the magnetic cores of transformers and other electrical equipment, leading to increased losses and reduced performance. DC current can also cause corrosion of grounding conductors and other metallic components. To mitigate the effects of DC current, it's important to use equipment that is designed to minimize DC current injection onto the neutral conductor. It's also important to use DC blocking devices, such as capacitors or inductors, to prevent DC current from flowing on the neutral conductor. Furthermore, the physical layout of the electrical wiring can have a significant impact on ground to neutral voltage. Long, unshielded wiring runs can act as antennas, picking up noise and interference from the surrounding environment. This noise and interference can then be coupled onto the neutral conductor, contributing to ground to neutral voltage. To minimize the effects of wiring layout, it's important to use shielded cables and to keep wiring runs as short as possible. It's also important to separate power wiring from signal wiring to prevent noise and interference from being coupled onto the signal wiring. In addition to the above factors, the quality of the electrical power supply can also have an impact on ground to neutral voltage. A poor quality power supply may contain voltage sags, voltage swells, and other disturbances that can contribute to ground to neutral voltage. To mitigate the effects of power quality problems, it's important to use power conditioning equipment such as voltage regulators and surge suppressors. Voltage regulators maintain a constant voltage output even when the input voltage fluctuates. Surge suppressors protect electronic equipment from voltage spikes and surges. Finally, it's important to remember that ground to neutral voltage is just one aspect of electrical safety. It's also important to ensure that the electrical system is properly grounded, bonded, and protected against overcurrents. A properly designed and maintained electrical system will provide a safe and reliable source of power for all of your electrical equipment. When investigating ground to neutral voltage issues, it's also helpful to consider the type of electrical system that is in use. The most common types of electrical systems are single-phase and three-phase systems. In a single-phase system, there is only one hot wire and one neutral wire. In a three-phase system, there are 3 hot wires and 1 neutral wire. Three-phase systems are typically used for commercial and industrial applications because they can deliver more power than single-phase systems. The type of electrical system can affect the way that ground to neutral voltage is measured and mitigated. In a single-phase system, ground to neutral voltage is simply the voltage difference between the neutral wire and the grounding conductor. In a three-phase system, ground to neutral voltage can be more complex to measure because the voltage between the neutral wire and the grounding conductor may vary depending on which phase is being measured. In addition to the type of electrical system, it's also important to consider the voltage level of the system. The most common voltage levels are 120 volts, 208 volts, 240 volts, 277 volts, and 480 volts. The voltage level can affect the severity of ground to neutral voltage problems. In general, higher voltage systems are more susceptible to ground to neutral voltage problems because the voltage drop on the neutral conductor is greater at higher voltages. When troubleshooting ground to neutral voltage problems, it's important to use the correct test equipment. A multimeter can be used to measure voltage, current, and resistance. A power quality analyzer can be used to measure harmonic currents, voltage sags, voltage swells, and other power quality parameters. An oscilloscope can be used to visualize voltage and current waveforms. It's also important to have a good understanding of electrical codes and standards. The NEC is the primary electrical code in the United States. The NEC provides requirements for the installation and maintenance of electrical systems. Other relevant standards include the IEE standards for grounding and power quality. It is necessary to have a deep understanding of the National Electrical Code Section 250.24, which covers grounded conductor brought to service equipment. This section is crucial because it dictates how the neutral conductor, the grounded conductor, is handled at the service equipment, directly impacting the ground to neutral voltage. 250.24 talks about grounding the grounded conductor, ensuring it is connected to a grounding electrode system. This connection is vital for providing a low impedance path for fault currents, reducing the risk of electrical shock and minimizing ground to neutral voltage. The code mandates that this connection be made at the service equipment or, for separately derived systems, at the source of the system. 250.24b addresses the exception to the rule where the grounded conductor may not be connected to the equipment grounding conductor on the load side of the service disconnecting means. This exception is designed to prevent parallel paths for neutral current, which can lead to circulating currents and increase ground to neutral voltage. It's essential to adhere to this exception to maintain a clean and effective grounding system. 250.24c discusses the sizing of the grounding electrode conductor, which connects the grounded conductor to the grounding electrode. The code provides specific requirements for the size of this conductor based on the size of the service entrance conductors. Properly sizing the grounding electrode conductor is crucial for ensuring that it can effectively carry fault currents and maintain a low impedance ground path. Understanding and complying with NEC section 250.24 is fundamental for minimizing ground to neutral voltage and ensuring the safety and reliability of electrical systems. Neglecting these requirements can lead to elevated ground to neutral voltage, increased risk of electrical shock, and potential damage to sensitive electronic equipment. It is also crucial to understand NEC 310.15, which covers ampacity of conductors. This section provides the guidelines for determining the maximum current in amps that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The ampacity of a conductor is affected by several factors, including the conductor's size, insulation type, ambient temperature, and the number of current-carrying conductors in a raceway or cable. NEC Table 310.15b16 provides the ampacity ratings for various conductor sizes and insulation types based on an ambient temperature of 30 degrees Celsius and no more than 3 current-carrying conductors in a raceway or cable. If the ambient temperature is higher than 30 degrees Celsius, or if there are more than 3 current-carrying conductors in a raceway or a cable, the ampacity of the conductor must be adjusted using the correction factors and adjustment factors provided in NEC Table 310.15b2 and NEC Table 310.15b3 respectively. The neutral conductor's role in carrying unbalanced current in a three-phase system directly impacts ampacity calculations. In a balanced three-phase system, the neutral conductor ideally carries no current. However, in reality, loads are rarely perfectly balanced, and the neutral conductor carries the unbalanced current. If the unbalanced current is significant, it must be considered when determining the ampacity of the neutral conductor. The NEC provides specific rules for determining when the neutral conductor must be counted as a current-carrying conductor for ampacity adjustment purposes. For example, if the majority of the load consists of nonlinear loads, such as electronic devices, the neutral conductor must be counted as a current-carrying conductor, even if the load is nominally balanced. Understanding and applying NEC 310.15 correctly is essential for ensuring that conductors are not overloaded, which can lead to overheating, insulation damage, and potential fire hazards. When troubleshooting ground-to-neutral voltage problems, it's important to consider the entire electrical system as a whole. The problem may not be isolated to a single component or circuit, but rather a combination of factors that are contributing to the elevated ground-to-neutral voltage. It's also important to remember that ground-to-neutral voltage is a dynamic phenomenon. It can change over time as loads are added or removed from the electrical system. Therefore, it's important to monitor ground-to-neutral voltage on a regular basis to ensure that it remains within acceptable limits.